Okay, so first we'll do the series, and it's pretty simple. But what we do is for each pipe section, you just write some resistor, sort of like this is what you're doing. Right, and then what we have is that we have all the flow rates have to be equal. So you have this one has to equal this one, has to equal this one, right, on and on and on. And this can be stated in terms of velocities and areas, but I'm going to go into that right now. And right, the goal of this is, right, just as you were saying, you want to have delta H is what we're trying to figure out what it is. So delta H is the difference head from here, we have H2. So H2 to H1, so that difference of head, right? When you work this out, what you end up, right? You work this out, and then you can see that this is really an R effective times flow rate squared. So that's sort of the biggest problem we have when it comes to these fluids, and these piping systems, we'd like to just do kind of like Ohm's law has so many nice properties because it's linear, because when you looked at Ohm's law, right, what was it? Right, change in voltage is the resistance, and then there's the current. So our current is flow rate, but it's squared. So this is really I raised to the 1, or right, this is the current raised to the 1's power, but in fluids you have this second power. And there's a lot of issues that come about with that when it comes to trying to solve these things with usual methods. So how do you get there? This is sort of what we've been doing this whole time, right? What are those resistance values you've been calculating, right? Those are the F factor, right? The friction factors and all these Ks that you've been looking at. They're really just flow resistance values, much like a circuit. So I think I wrote this all out, so it's kind of nice to sort of see. I could have N sections of pipes, and you could say, well, the change in head, sum of all the majors, plus sum of all the minors. So you should understand from the other ones that right here are some minor losses in here. Right, these are minors because these are expansions and contractions. So those have to be included in there. And then, you could even have a valve in something like this. So that's also going to be in there. And what are the major sections? The major sections are the long straight sections of pipe. So this is kind of the clearest example of why you would want to ever calculate those effective lengths. Was you just write one thing. Length of that pi, I, di, right? Say I have N of these and major sections, and we could have like how many minors? M minor losses that you add up. This is M, and what do we have there? Our formula say it's K, I. So this M, this is N. I'm just writing out whatever in series pipes I have. I know that the head losses, majors, and minors. I've just written out the formulas of these. Now, this is a reason why you'd want to calculate these effective lengths, if you remember. Because if I calculate the effective lengths, everything would look exactly the same, right? Then I would have this, I could turn this into looking something like this. Comma I, di, right? Right, so if I want to calculate effective lengths when it comes to these resistance coefficients. And if you do that, right, then everything, it just looks exactly the same with these friction coefficients, the lengths, the diameters, and that chunks down at your whole piping system. Now M plus M components I have n plus the m's, but, right, so some of these are effective lengths. So m of these are actually effective lengths, but you just have you just have one form you have to keep track of, right? And then you can see that you can express this in terms of flow rate. If you do that, you can see where this is all going. All I'm doing is just writing velocity in terms of flow rate, and you'll see why. This turns into a fifth. Here, there. G. Right, so when you replace the flow rate with all those velocities, you get these expressions right here, and you can see how this is an effective resistance to pipes flowing in series. The one issue you should understand is it's not that simple just because of what these F's are. The F's come from either the F's are coming from Reynolds numbers, right? So the F's are also a function of the Q that has to happen for this. So it's a little more, right? It's not as simple as just a bunch of scalars. You have to do things. And that's why you have these iteration type problems where you're trying to figure out the correct velocity given this thing right here. But we'll go into that sort of example. But for pipes in series, this is what you just need to look for, right? You're really just trying to figure out what the effective resistance is to that, right, to those pipes in series. So all the calculations right here, this is a given, and this will just pop right out, the head loss due to the viscous losses. Right, notice this is also only true if you have, right, if you have no change in height. If you have change in height, all these Bernoulli equations at different junctures, right, will change. But any change in height, you just write down the Bernoulli's equation, and then you can solve for that added energy or lost energy due to gravitational forces. Okay, so then I'll go over, I guess, what you can do with an equation written out like this.